My name is Sarah Dean, and this is the third video in a video tutorial series on introductory medical statistics. This is a continuation of material in a previous video where I introduced the concept of cost-benefit analysis in medicine and demonstrated the important differences between relative and absolute risk. In this video, we'll go into more detail on how to calculate different absolute and relative risk measures, starting simply with absolute risk and relative risk. All right, so absolute risk, or AR, is just the raw risk of an adverse outcome. So if you have a group of people, you simply take the number of people who had the negative outcome and divide by the total number of people in the group. And you interpret this value as the likelihood of experiencing an adverse outcome in a certain situation or from within a certain group. And it's usually expressed as a rate, like 1 chance in 10,000, or a percentage, which is just the rate in 100. Relative risk, or RR, compares the risk of adverse outcome between two groups. So in the example from the previous video, we could compare the absolute risk of neonate mortality in a hospital to the absolute risk of neonate mortality when birthed at home. Or we might compare the absolute risk of disease in a vaccinated and unvaccinated group. Relative risk is the ratio of absolute risk between the two groups, and it tells you how many times more likely it is to experience an adverse outcome if you belong to group 1 versus group 2. Typically, group 1 is a group exposed to a therapeutic treatment or to a hazard. So we call it sometimes the exposed group. And group 2 is the unexposed group, or the group that represents normal and natural conditions. Usually in medicine, we are comparing two groups because we want to know how different situations, different treatments, different hazards affect human health. Relative risk is one simple way to do that, but there are others, some that work with absolute differences between groups and some that work with relative differences between groups. In any experimental study in medicine, you will have a treatment group and a control. The treatment group received some intervention. You compare how people in the treatment group fare relative to the people who represent the baseline, otherwise known as the control group. In this hypothetical example, I'm keeping things very general. All right, so you are doing a study on how well a particular medicine helps with a medical condition. The treatment group is exposed to the experimental medicine, so we call it the exposed group. And in this case, the exposed group has 16 people in it. The control group is unexposed to medicine, so can be called the unexposed group. The unexposed group also has 16 people in it. In our example, in the treatment group, 4 people have an adverse outcome. So that's indicated by the people who are darker. So the darker people have some adverse outcome, right? And in the control group, 8 people had an adverse outcome. This means that the absolute risk of adverse outcome in the treatment group is 25%, right? Because 4 out of 16, which equals a quarter, or 25%. So 1 out of 4 people, or 25% of people, had an adverse outcome in the treatment group, while the absolute risk in the control group is 50%. So you can see why we need a control group. Just because some people get better with treatment or some people have an adverse outcome with treatment doesn't mean the treatment is responsible. Some people get better or worse on their own without any kind of treatment. To know whether there are any effects of treatment, you have to compare outcomes of treatment to what would have happened naturally. This data shows us that there are fewer adverse outcomes for people taking the medicine relative to people not taking the medicine. So there is a risk reduction. But how big is it? Absolute risk reduction, or ARR, is the difference between the absolute risk of adverse outcome in each group. In other words, the AR of the control group minus the AR of the treatment group. So remember, the AR of the treatment group, we lost my notes here, but that was 25%. And the AR of the control group was 50%. So to figure out absolute risk reduction, we take the original risk from the control group and we subtract the risk in the treatment group. And we're left with 25%. Now, of course, the goal of a medicine is to reduce risk, but remember that even medical treatments can cause negative outcomes. So you have to be open to the idea that there might be a risk increase instead of a risk reduction. Also, there are medical studies on exposures to toxins or hazards, which cause a risk increase. If you get a negative number for absolute risk reduction, it means you actually have an absolute risk increase. And you could calculate that more directly by flipping the exposed and unexposed groups in the equation, as indicated in the equation for ARI on the left. Some other jargon you might come across is incidence. The incidence is the rate of people experiencing the outcome of interest. The incidence of the adverse outcome was 25% in the treatment group and 50% in the control group. So the same as AR in this case. But often, incidence is expressed in terms of the whole population instead of just a small sample like this, and also includes a time element. For example, 5 in 1,000 people over the course of a year. Another very useful medical statistic is the number needed to treat. This statistic tells you how many people must receive treatment for just one person to benefit. The calculation is simply the reciprocal of absolute risk reduction. From the previous slide, ARR was 25%. That's actually the same as 1 in 4, right? So that means that the number needed to treat is the reciprocal of that, which is 4 over 1, which just equals 4. And this means that 4 people must receive treatment for one person to improve who wouldn't have improved naturally. Let's dive into that a little. Some people get better without treatment. Some people do not get better even though they received treatment. So in both groups, you expect to find some people who experience adverse outcomes and some who do not. But the proportion of the adverse outcomes is different because, at least in this case, the treatment has an effect. The number needed to treat is how many people need to take the medicine to change the natural outcome for just one person. Conversely, the number needed to harm is how many people need to be exposed to some hazard before one person becomes negatively affected who wouldn't have had that outcome anyway. And number needed to harm is calculated from ARI, or absolute risk increase. All medical interventions have negative side effects. So you can measure the number needed to treat for the positive outcomes of a medicine and the number needed to harm for the negative side effects of that same medicine, and then compare them to see if the medicine does more good than harm. These are measures of risk versus benefit, which contribute to cost-benefit analysis. Like all statistics, they seek to separate exposure effects from the natural course of things and random chance. Relative risk reduction and relative risk increase are extensions of relative risk, which we talked about earlier. Remember the difference between absolute risk measures and relative risk measures from our home birth versus hospital birth example in the previous video. RRR and RRI indicate how big the change in risk was after exposure to a hazard or treatment in comparison with the original risk. It is expressed as a percentage of the original risk. Remember, if the original risk was already very small, even a small change in absolute risk can result in a large change to relative risk reduction or relative risk increase. To calculate RRR, you would take the absolute risk reduction and divide by the original absolute risk, which is the AR for the control or unexposed group. So we've already calculated that this medicine causes a 25% absolute risk reduction. And to figure out how big that is proportionally to the original risk, we simply divide it by the original AR. Remember, the risk of adverse outcome in the control group is 50%, which means that the relative risk reduction is the ARR, or 25%, divided by the original risk, which is 50%. And that is, 25 out of 50 is 50%. This means that the risk of adverse outcome in the treatment group is half that of the control group. Now, you can use counts instead of percentages if you prefer, and the results come out the same. There's 8 people with adverse outcomes in the control. There's 4 people with adverse outcomes in the treatment group. So we could do 8 minus 4. That's the incidence exposed minus the incidence unexposed, divided by the incidence unexposed, which is 8. And that equals 4 out of 8, which is still 50%. And by the way, INC here, that means incidence. As discussed in the previous slide, you could replace incidence with AR. And actually, you can only use count here because both the control group and the treatment group are equal size. You really should use incidence, which is, of course, the rate or the ratio in the whole group. You should always report ARR and RRR together. Let's look at one more example to see why that is important. A hypothetical drug reduces the risk of colon cancer from 1 case in 5,000 to 1 case in 10,000 over the course of 1 year. All right, so what is the absolute risk reduction? To figure that out, we have to take the difference between 1 in 5,000 and 1 in 10,000 and convert that to a percentage, which you can do on a calculator or you could do it like this. All right, so 1 in 5,000 is the same thing as 2 in 10,000. So ARR will equal 2 in 10,000 minus 1 in 10,000, which equals 1 in 10,000, which equals 0.0001, which equals 0.01%. So what is the number needed to treat to prevent colon cancer? Remember, the number needed to treat is the inverse of ARR. Absolute risk reduction was 1 in 10,000. So the inverse of 1 in 10,000 is just 10,000. This means that 10,000 people must take the drug to prevent one person from getting colon cancer. So the number needed to treat is useful because it puts the practical implications of a treatment into perspective. All right, so what is the relative risk reduction? Remember, to find the relative risk reduction, we take the ARR and divide by the original risk in the control group. Now, the original risk in the control group was 1 in 5,000. So I'm just going to convert that to a percentage so that everything is in the same units. So 0.02% is the absolute risk in the control group. And we calculated the ARR up above here. That's 0.01%. So the relative risk reduction is going to be 0.01% divided by 0.02%. 0.01 divided by 0.02 is 50%. So what this shows is that you can have an absolute risk reduction of 0.01% and a relative risk reduction of 50%. You can see how reporting only one of these two risk reduction measures would be misleading. Reporting only relative risk reduction might cause readers to exaggerate the impact of a drug, while reporting only absolute risk reduction might cause readers to underestimate the impact of a drug. The low absolute risk reduction reflects the low probability of getting colon cancer in the first place. But if you happen to be part of that small group that was going to get colon cancer naturally, this drug has a huge impact on adverse outcome. What if after doing this analysis on the benefits of the drug, you next looked at the risk of negative side effects? What if the absolute risk of the negative side effects is higher than 0.01%? Every intervention introduces risks. Sometimes they are worth it, but sometimes they are not. What you need to do when conducting a cost-benefit analysis is to consider relative and absolute risk of disease, as well as of side effects, and then compare them. You might brainstorm about the dangers of not reporting both absolute and relative risk, and these dangers might differ for different situations. The difference in these two statistics is the difference between absolute values and ratios. They each tell you different parts of the story, so be sure you understand which part of the story you are learning. Relative risk is the risk of a negative outcome with exposure relative to the risk without exposure. And absolute risk provides a sense of scale, or the actual number of people affected. And it's used to calculate the number needed to treat or the number needed to harm. There's just one more risk measure I want to look at before we end this video on risk assessments. It's more complicated than what we've already covered, but you will see it in medical research quite a lot, so it's worth going over. An odds ratio is similar to relative risk, except that it does not require you to have data on incidence of adverse outcome in the whole population. So when we were calculating relative risk, or RR, we didn't have data on the whole population, but we were able to estimate incidence in the whole population from a random sample. In one example, we had a control sample of just 16 people, and 8 out of 16 of them had the adverse outcome, or half. If we actually chose a random sample, then our sample of 16 most likely reflects people in general. But for rare diseases, a random sample might by chance not include any diseased individuals. Take our hypothetical colon cancer example, where 1 out of 5,000 people get colon cancer and only 1 in 10,000 people in the treatment group got colon cancer. If we don't have the money or means to conduct a study with hundreds of thousands of people and instead have a study with only 100 people, it's very likely that we won't get anyone with colon cancer in either the treatment or the control group, making it impossible to measure treatment-related risk reduction. This is a situation where we would opt to use odds ratios instead. Odds ratio calculations allow for non-random samples where a disease is rare. Keeping with our colon cancer example, we would intentionally select diseased people. We'd seek them out. And then we would determine how many of them were exposed to a particular treatment or a particular hazard of interest. So, for example, out of all the diseased individuals, how many were exposed to the medicine we're studying? Next, we would take a random sample of the healthy population and see how many are exposed and not exposed to that same treatment or hazard. To calculate the odds ratio, we would determine the ratio of disease to healthy people in the treatment group, and then we would do the same for the control group, and then we would ratio the ratios. So the difference here between relative risk and odds ratio is how we do the sampling. With relative risk, we built exposed and unexposed groups, and then we counted who was healthy and diseased in each group. With odds ratios, we build diseased and healthy groups from the general population, and then we count who was exposed and unexposed to the hazard or treatment in each group. So let's do the calculation with some data. This is an example from the Wikipedia page for odds ratio. So suppose a radiation leak in a village of 1,000 people increased the incidence of a rare disease. And here is the data from a random sample of healthy people and from intentionally selected diseased people. So the odds of getting the disease if exposed equals the diseased individuals in the exposed group divided by the healthy individuals in the exposed group. And in this case, that's 20 divided by 380, which is 0.052 or 5.2%. And the odds of getting the disease if not exposed equals the diseased individuals in the not exposed group divided by the healthy individuals in the not exposed group. And in this case, that is 6 divided by 594, which equals 0.01 or 1%. So the odds ratio is the ratio between the odds of getting the disease if exposed and the odds of getting the disease if not exposed. So in this case, that's going to be 0.052 divided by 0.01, which is 5.2. And just note, you can work with the percentages or you can work with the raw numbers. It really doesn't matter as long as you maintain consistency between all your steps. So you interpret this the same way you would relative risk. You are 5.2 times more likely to get the disease if exposed to the radiation. If OR equals 1, it means disease is equally likely in the treatment and the control group, which also means there's no relationship between exposure and disease. When OR is small, it means that disease is negatively correlated with exposure, or it's less likely in the exposure group than in the control group. You would expect to see this if the exposure is therapeutic. When OR is high, it means that there's a positive relationship between exposure and disease, or the disease is more prevalent in the exposed group, and you would expect to see this if the exposure is a hazard of some kind. OR and RR calculations are nearly identical when a disease is rare. And this is because RR, relative risk, works with the ratios between diseased people and the total number of people, while OR looks at the ratio between diseased people and healthy people. I'm not writing the full equations here. I'm just writing the ratios that the two metrics work with. By definition, a rare disease is a disease for which the number of healthy people is almost identical to the total number of people, So in the cases of rare disease, OR will give you essentially the same value as RR. And that concludes video 2 in this video series on introductory medical statistics.